All right, my goal with this video is rather ambitious. I want to develop the ideas of electrical energy, and we're just going to talk about potential energy, and it can be turned into kinetic energy. The concept of electric potential, the potential difference, which is the difference between two electric potentials, and the related idea of voltage, which is essentially potential difference. Okay. So we have two parallel plates. Just if you looked at the previous example on forces, electric force between here, that's the same. I use the same field. You have two plates. Here's your electric field between the two plates. And if I placed a positive charge somewhere inside this field between those two plates, let's say I place it some distance d from the negative plate. Well, if I place that there and I hold on to that charge, you all know that it's being repelled by the positive plate and attracted to the negative plate. It has potential energy. I'm holding on to it. It has potential energy, just as when I hold on to my whiteboard marker, it has the potential energy, if I let go of it, to accelerate downwards. This has the potential energy to accelerate, in this case, to the right. So that has potential energy. As it accelerates, if I let go of it, as it accelerates to the right, it will look through the distance d. The field will do work on it because it applies a force. So the field will do work. This will lose its potential energy and gain kinetic energy. Before I get into that, I want to define electric potential. See, electric potential energy is fairly difficult to measure. Gravitational potential energy in joules is not, but electrical potential energy actually is. So instead we talk about electric potential, which is potential energy per unit charge. Potential energy per unit charge. Potential energy per unit charge. And we use the letter V. It's an uppercase V. It'll be measured in volts. An uppercase V, that's electric potential energy. Defined as potential energy, we use a U, remember, for potential energy, per unit charge. The nice thing about all of these values is that they are scalar. They're not vectors. This is a vector, and in fact, it can get rather nasty, dealing with electric fields. And of course, electric force is a vector. But these are scalar. Energy is a scalar quantity. Okay, so I want to talk about a few things here. I want to look at what happens to its potential energy as it goes from one side to the next. You know that as it loses potential energy, because again, it's going to go from UI to UF, and UF over here would be 0 once it gets to the negative plate. So as it changes its potential energy, it's going to gain kinetic energy. In fact, energy is conserved. And so you can either use a delta K, or if you want to put a KE for kinetic energy, that's fine. But the change in the potential energy that it loses would be the kinetic energy that it gains. Now you can see that if I multiply both sides by Q here, that U equals QV. And so frequently you'll see a couple things here where delta U equals Q delta V. What is delta V? That's the difference between two electric potentials. That's potential difference, delta V. That's also the idea of voltage, delta V. When you think of voltage, think of potential energy. They're very closely related. You can also see that the change in kinetic energy There's a negative sign here. I'm just going to place it here. Because it's those two, negative sign in front of one of them. Negative Q delta V. We more often than not deal in absolute values when we look at these things. Those are just some conceptual points. One other thing I want to point out, remember that work when work is done, kinetic energy may change. If the network is not zero, you'll have a change in kinetic energy. And this is called the work kinetic energy theorem. We saw it last semester. Well, in this case, the work is done by the electric force through this distance d. All right, so the electric force, there's a force acting on this, F, and it acts through this distance from here to here. So that equals delta K. And you also know that the equation for force, remember the equation for force is Q times E. And so Q times E times D equals delta K. I'm going to take this and put this over here. Again, that equals delta K, delta K, delta K. So Q, whoopsies, Q, E, D is negative Q delta V. Your Q's cancel. An equation that you run into on occasion is that delta V, put the negative sign on the other side, equals negative E times D. And again, we normally deal with absolute values. But all this means is that as this charge, as a positive charge is accelerated through a voltage, through this field, it loses its potential. Now, if you had a negative charge, everything would be opposite. Positive charges always accelerate from higher potential to lower potential. Totally makes sense. Just like my whiteboard marker accelerates from a higher potential to a lower potential. Positive charges accelerate from a higher potential to a lower potential. They go downhill, if you will, all right, when you let go of them. Negative charges do the exact opposite. It's like a negative charge is analogous to something that if you let go of it, it miraculously accelerated uphill. Negative charges accelerate towards towards higher potential. So negative charges always seem to do the exact opposite thing of positive charges. All of these things are originally written for positive charges. So this positive charge accelerates towards the lower potential. Okay. Let's just put some numbers in here so we can calculate something. All right, here's what I want to do with this. I want to calculate the potential difference, the voltage, the potential difference between the points when the charge is at this initial position. That's 3.7 millimeters from the negative plate, comparing it to when it's at the negative plate. So what's the delta V for that? Then that'll be in volts. And I want to calculate the change in its potential energy and also its change in kinetic energy. So let's start here. Delta V equals negative E times D. So that's negative 795 newtons per coulomb times 3.7 times 10 to the negative 3. And let me get my calculator out here. So that's negative 795 times 3.7 times 10 to the negative 3, which that's negative 2.94, negative 2.94 volts. Again, that potential difference and electric potential are measured in volts, uppercase V. That's named after Alexandra Volta. Alexander? No. His last name is Volta. I forget his first name. Sorry. Well, delta V, by definition, just so you know, it's kind of as an aside, delta V is just the final potential minus the initial potential. It's just the change in potential. It's the change in electric potentials, giving us the potential difference, or voltage. So if you're asked to find the initial potential, for example, electric potential, well, the final is 0 because it ends up at the negative plate. And a positive charge ends up at the negative plate. It's done. It doesn't have any potential anymore. It's like dropping my whiteboard marker. It ends up on the floor. It's used up its potential energy, if you will. So its final is 0. So if this is negative 2.94, and that's 0, then what's the value of VI? Because if I ever asked that of you, what's the initial electric potential? Well, it's going to be, add that to the other side, subtract that to the other side, it's going to come out to be 2.94 volts. All right? 0 minus that gives you negative 2.94. Okay. We also know that if U equals QV, we know that delta U would equal delta Q delta V. So given that the charge right here is 3.2 nanocoulombs, that's 3.2 times 10 to the negative 9 coulombs, and delta V is negative 2.94 volts. When you multiply that out, I'm looking at my numbers. Did I get that right? I hope so. Did I get that right? Yeah, it looks right. Okay, so if I got it wrong, I apologize. I already have this on my calculator. Negative 2.9415 is what that actually is. Times that, so that's what, 3.2 times 10 to the negative 9. Yeah, okay, hold on. Negative 9. So I get negative 9.4, negative 9.4 times 10 to the negative 9 joules. That's the change in the potential energy, the change in potential energy of this charge. It's negative because it's losing potential energy as it accelerates to the right. What's its gain in kinetic energy? By the way, when it gets to the negative plate, it has 0 potential energy. So what's its initial potential energy? Just U, I, not delta U, but U, I. It must be positive 9.4 times 10 to the negative 9 joules. It's got positive 9.4 times 10 to the negative 9 joules here. It loses it all on its way to this negative plate. What's its change in kinetic energy? Well, its change in kinetic energy is equal and opposite to its change in potential energy. Energy is conserved, at least until it hits the plate. So that's going to be minus a negative, which is positive 9.4 times 10 to the negative 9 joules. Okay? Again, if I ever asked you to find like just the initial potential energy, well, just remember, you've got the change. Remember that delta U is final minus initial, and the final is 0. And so the initial would be positive